All right, team, welcome back to lecture at 6, excitatory inhibitory neurotransmitters. It's exciting. Let's do this. And so here, what you folks are seeing are a page of excitatory neurotransmitters and inhibitory neurotransmitters. You need to memorize these transmitters, right? Is because we're going to now use them in a functional way on the homeworks, on the exams, so that you folks can practice and understand how brain signaling works. Now let's talk about these neurotransmitters. So if you are an excitatory neurotransmitter, that means when you send your neurotransmitter and when that neurotransmitter then binds to its postsynaptic neuron, then what's going to happen is that cell is going to depolarize. Okay? And folks, remember, don't forget now, depolarize means you become more positive in your membrane potential. Okay? Now, if you're an inhibitory neurotransmitter, these neurotransmitters inhibit or stop a signal from being propagating in that second neuron. So these cause the cell to hyperpolarize. Okay, so look at our scenario here. We have 3 cells. And in the previous lecture, I drew you folks something similar, right, to these 3 cells. So I have one big yellow neuron, and it is receiving signals from this red neuron and this blue neuron. And I'm sorry if some of you folks are colorblind. I keep forgetting not to say colors, but every other semester I do get people who are colorblind. So I will say the color, but then I'm also going to move my pen around. So look for these signals just so I can make sure that everybody is understanding what I'm trying to teach her. Now, if you look at this red neuron that is on top, okay, is that look at the electrode. Where is the electrode? You see it? It's right in this axon here, right? And so here we can see if we're following this red line or the top line, okay, so follow my little cursor here, is that I can see that an action potential happened in this area is because I can see depolarization occurring, yes? So I have depolarization, repolarization, hyperpolarization, and then going back to resting. So that's the red voltmeter. Now, if you look then at what's going on in the yellow neuron here, this big neuron, you can see is that because the red neuron is a positive signal, that means that it secreted one of these excitatory neurotransmitters, and it caused now positive charge, whatever ion that may be, sodium, calcium, there's some others that I can't remember right now, that they will come rushing in, and then I'll have positive charge inside of the cell. Hence, this increase in voltage, yes? This increase called EPSP, which I will address in the next slide. Now, look at the blue neuron down here. It's this bottom small neuron. Again, I have the same pattern. I have electrode in the axon, and then I have an electrode in the yellow big neuron cell body where there's the synapse. Okay, so here again I can see the action potentials traveling down this blue neuron because I can see depolarization, repolarization, and the hyperpolarization. But I know that it has to be secreting some type of an inhibitory neurotransmitter, because if GABA or glycine binds to their ligand-gated channel here, then I'm going to have a whole bunch of negative ions, chlorine, come in, and then I have a negative charge, or I can have positive charge ions come out, which would also lead to a negative charge, okay? And you can see, look at the voltage now. It goes down. It hyperpolarizes, yes? IPSP. So remember, in the cell body in the dendrites, the signaling is called graded potential. So if it's a positive one, it's depolarized, and if it's a negative one, it's hyperpolarized. When we get to the axon, the nomenclature, oh, that was a chemistry word, but the wording is different, right? Is that I have depolarization, repolarization, and then hyperpolarization, okay? Now, memorize these neurotransmitters because we are going to work with these. Okay, let us move on. All right, let's talk EPSP, IPSP, right? So EPSPs are signals called excitatory postsynaptic potentials. And they're excitatory. So remember, right? If I'm going to excite a neuron, then I have to have the capacity to depolarize it. Depolarize. Because that positive charge, right, inside the cell is what causes the excitement, right? Is because if that cell now is going to pass on that message, it has to have enough positive signal that's going to hit that axon hillock for the threshold to be met. Now, inhibitory, remember, this is if I hyperpolarize, become more negative in my graded potential. All right, now let's look at some graphs. Don't hate the graphs. Even if you hate graphs, I spent years hating graphs, and then I embraced it. And then now I'm okay. Now, okay, so again, you look at the x-axis, you look at the y-axis, you get your recipe, you repeat your recipe over and over and over. And what I'm seeing is over time that if I get a signal right here, that's the red, is that I'm having a charge that becomes more positive. That's EPSP, right? Now, EPSP, then by definition, is a graded depolarization signal. And it can now move the membrane potential closer to the threshold for firing and action potential, right? So this is just worded in the textbook way. I described everything up here in Sherry language. This is the textbook way. And it's good for you folks to be familiarizing yourself in different ways of how to state the same sentence. This is why rewording the lecture in your own notes brings your understanding to a different level. All right, now, how do I get EPSP signals, right? Usually, if I open up a sodium channel, sodium can come in a cell. That is the main way. There's calcium, there's other ways, but sodium is the main player, okay? Now, if we're going to talk about EPSPs, we're going to talk about IPSPs, right? So look, my cell is at rest, resting potential. I get a signal, and what is a signal? Is when neurotransmitter that is released from a presynaptic neuron is going to bind to this particular cell and cause some ligand-gated channel to open, right? And we're going to move ions. That's all it is. So I receive that neurotransmitter. It binds to its receptor, and therefore this graded hyperpolarization will cause then the charge to become more negative. And so this would inhibit, right? Inhibit a cell from reaching threshold at the axon hillock. Now, there's different ways you can get an IPSP signal, right? So let's talk about two different ways. Let's talk about chlorine and let's talk about potassium, because these are the two main ways where we can now have IPSP signaling. So if chlorine flows in, right? So let's just draw that right here. So if I have a cell, let me change my pen color because that's just a lot of red. So give me a second. I'm going to choose purple, and I'm really hoping that you folks can see purple. I'm using purple because I can see it really well on my screen, but that doesn't really mean that you can see it. But if you can't see purple, shoot me an email so I can start using a different color. All right, purple. Here we go. Now, if chlorine or chloride ion flows in, right? So if I have chloride ion, it's a negative ion. And if it flows in down its concentration gradient, then that's going to cause this potential in this area of the cell to be negative, right? Now, let's do another example, right? If I have potassium, okay, and we did this is unit 1. When potassium leaves, I'm losing a positive charge. And if you lose a positive charge, then that can also cause the membrane to be negative, okay? EPSP, IPSP. All right, so let's put it all together now. Remember, I told you folks that a single neuron has hundreds of other neurons talking to it and up to 200,000 neurons talking to it. Like, that baffles my mind. So I just have to stop thinking about it, because in my mind, I start thinking about if 200,000 people were talking to me all at once, and based on everything that they were saying at the exact same time, I had to make a decision on what to do. Oh my God. Yeah, that just makes me want to go to sleep. Okay, so that's what's going on in the cell, in your neurons though, right? So I have some neurons receiving neurotransmitters that cause EPSP. Some of them are causing IPSP, right? So I have all these ions, and let's draw this here, right? So if this is my main neuron, and if I'm receiving signals, and I don't want to draw too many synapses because then we'll be here all day. Okay, and then if this is the axon hillock, I'm getting positive signals coming in. I'm getting negative signals coming in. I'm getting negative signals coming in. I'm getting negative signals coming in. Remember, all of these ions are just going to diffuse down their concentration gradient. They're going to move. Some of them are going to get kicked out because there's ATP pumps, right, that are constantly maintaining the resting potential. Some will get kicked back out. Some will move towards the axon hillock. So whatever net charge reaches the axon hillock, that's how the cell determines what to do based on all the messages it receives. That's what we call summation, right? Is because I'm getting the summation of all these charges coming to the axon hillock. And if I hit threshold, then bam, I can have an action potential. Okay? You folks good? Summation. And summation is the addition of all the charges of a graded potential. Okay? All right. That's it for this lecturette. Come back because we're gonna start talking about long-term potentials, and we're gonna close that with that, and it is just an amazing topic. All right. Come back.